Hi, my name is Jez Heath. I'm the UCWEAR Programme Lead for Leakage. Reducing water leakage is vitally important to the water industry and to our customers as well. By 2050, we're predicting that due to climate change and increased demand, we're estimating the supply-demand gap is going to be nearly 5 billion litres a day. And to help meet that gap, all the water companies in the UK have committed to halving leakage by 2050, and in some cases sooner than this. But I'll be honest, as an industry, we're really struggling at the moment, largely due to the recent dry, hot summers. Currently, only about 20% of UK leakage experts believe that the industry will be able to achieve the required reduction. Now, there's no magic bullet that's going to solve leakage. And it's important to understand as well that there's no lack of solutions at the moment that companies can use to reduce leakage. However, what we typically lack is a strong understanding of which particular solutions will work in which specific scenarios. It's like having a medicine cabinet which is absolutely stock full, but you need to understand which medicine is most effective in dealing with which specific disease. So this project has tried to identify which factors, like water pressure or pipe age, most impact leakage in a small area. And also beyond that, coming up with an action plan that allows water companies to target that leakage most effectively. As you'll hear, it's been very, very successful and has long-reaching impacts for how we manage leakage in the UK. Let me hand over to Rhys Durham, Senior Consultant at Artesia, who's going to explain more about how they carried out the project and also its findings.
Thanks, Jez. Today I'm here to talk about this project recently delivered alongside David Consulting. The project was structured around 3 key stages, which you can see here. Stakeholder engagement, which was targeted towards understanding the key factors and techniques we should be focusing on in the project. Then data analysis of data at district metered area resolution and developing a Bayesian networks modelling approach. And finally, combining the expert insight and data analysis, grouping DMAs into a set of scenarios with practical playbooks. We distributed a survey to a variety of stakeholders, and one area of focus of that was the factors that affect DMA leakage, which drove our priorities for future phases of the project. The chart on the right represents the importance of different types of data, with respondents clearly feeling that physical characteristics and management of the network were very important, whereas customer factors and demographics were consistently ranked lower. We also focused on leakage interventions. These were structured around the PALM framework and began to establish what works well and where. And finally, we asked what format, content and variety people would find most valuable for the playbooks that we produced. For this project, we collected data from participating water companies as well as open source data that we could use consistently for all companies. We grouped company data into 3 cohorts: time series data like flow, pressure and leakage, static characteristics that very rarely change such as pipe materials and sizes or DMA boundaries, and variable characteristics that might vary slightly year on year. Company-specific data from 5 companies across 6 regions passed our QA process with a sample of more than 3,000 DMAs ultimately being used. Open source data was also really valuable, allowing us to assess additional variables and do it with consistent data for all companies. Following data collection, we performed exploratory data analysis. This is essential to understand the data and highlights a lot of key insights that could be missed by just going straight to modelling. I'm going to talk through some of the major highlights. The first obstacle when analysing leakage is normalisation. Large DMAs typically leak more than small ones, so accounting for this is very important, and how you do it can make a big difference to the results. The most traditional metrics are normalising by mains length or the number of connections. These are simple and intuitive, but as the top 2 charts show, it can create a bias between urban and rural areas. We chose the Curly metric as the optimal route. Curly combines the 2 other metrics into one less biased metric. This has been used around the world to compare leakage levels, but this is the first time at individual DMA level. While it's slightly less intuitive, we found it less balanced and think there's a lot of opportunities for using this when analysing leakage going forward. One of, if not the most important variables in leakage is known to be pipe material, which came through really clearly in the stakeholder engagement exercise. In the DMAs we received, we found that polyethylene and cast iron, followed by PVC, were the most dominant materials. However, analysing materials is really challenging since most DMAs contain a mixture, making it difficult to evaluate minor materials. You can see that whilst some of the groups show a minor trend, cast iron pipes in urban areas is the only scenario where we see a statistically significant difference. This is a key finding, and hopefully this can aid water companies going forward with prioritisation of replacement and rehab. Pressure is another variable that we investigated. We can see there's a clear positive trend across regions and almost all of the normalisation techniques. Following exploratory data analysis, we approached the modelling task with a subset of the key variables. Considering the factors on the right, we chose a probabilistic approach using a Bayesian networks model. This is ideal for identifying the likelihood of the different variables impacting leakage. On the left, we can see the trained Bayesian network. The arrows indicate the dependencies and relationships between variables, whilst the numbers show the natural probabilities in the dataset. This means that 23% of the DMAs in our sample were classed as high leakage. We can also test different scenarios. For example, if we fix pressure to be high, we can show that high pressure DMAs are 43% more likely to be high leakage. Finally, we took the learnings from the stakeholder engagement and data analysis to develop practical playbooks that can be used to improve ALC and benchmark DMA asset health. Companies can enter information on their estate with a leakage severity score that's based on our modelled outputs. Each DMA is then allocated to a specific scenario based on its characteristics, and suitable recommendations are outputted. Creating playbooks for each DMA would be very challenging, and therefore we developed 13 cohorts, which we call scenarios. This is primarily based on our modelling, but we also considered what factors would meaningfully change the way that DMA is managed. With these scenarios, we were able to consider the optimal interventions for each of these areas, and that enabled us to detail what works well and where. Each intervention is ranked against others for that specific scenario. We've completed this sheet with a full set of default values, but each company is different. So this is a fully editable Excel sheet where users can map the interventions however they wish. We've considered 5 prevent, 9 aware, and 10 locate interventions. We haven't ranked mend interventions in the same way because we felt that the optimal decisions would depend on different factors. We've also developed specific winter actions that might be deployed in response to a freeze-thaw event. They're not ranked in quite the same way, but we've highlighted which scenarios are suitable for each of those actions. Following data entry and intervention mapping, there are 2 output views that are available to users of the tool. The company view allows companies to benchmark their DMAs against the sample provided, and you can observe the average level of leakage, connection density, age of the network, and other details, both in the table and in the chart on the left. The right-hand side allows companies to understand which scenarios they have more or less of than other companies, and that can guide companies towards interventions that are well suited to their areas. The second view that's available is focused on a specific DMA. The drop-down list allows the selection of a DMA based on the data loaded into the tool. This highlights the key DMA metrics and how they compare to the wider sample and values that are entered by the user. The top right section highlights the scenario the DMA is in and the key recommendations based on the intervention matrix.
I hope that you found this project as interesting and as impactful as I have. I believe that this project is going to greatly assist us in managing leakage in the short term. But more than that, it provides us with a way of comparing different water company distribution networks so that we can better understand why some leakage interventions work in one company but not in another. And that will help us better invest in the future to driving down leakage. I'd like to particularly thank both Artesia and Dayworth Consulting for delivering such a well-researched and I have to say fascinating project.